Here's some suggestions on how to take a look at problem number 53. Problem number 53 deals with two parallel and oppositely charged plates that are about 2 centimeters apart. And they say something in there like an electron is going to be launched between these two plates here at 45 degrees. And to give you some other information, so 45 degrees is some speed v. And it wants to know what the maximum speed is, so it won't hit the negative plate. So it's going to sort of fly in some motion here, but we don't want it to hit the negative plate. What would the speed have to be? In order to get this problem sort of to work out here, you have to think a bit about what it's asking about. It has these two parallelly charged planes in the problem here, two equally charged planes. And what do we know about one plane? So this is a big plane of charge here, and it's sort of drawn at maybe 3 dimensions. There's a bunch of positive charges all over this thing like that. Positive charges as far as you can see. The electric field at any point around the plane there is sigma over 2 epsilon here, where sigma here is a charge density. Now it's a 2-dimensional charge density here, so the units of sigma here are going to be coulombs per square meter. It's not lambda, it's sigma now. Okay, and this is the result here. So what happens then if you have 2 plates next to each other like this? Well, here's sort of what the electric field picture looks like then. This is a negatively charged plane, so it'll have electric field lines sort of going into it like that. This is all due to the negatively charged plane. So these green lines here are due to the negatively charged plane. And notice they're going into it, into negative, out of positive. Well, we also have this positively charged plane. We know there's electric field lines coming out of it. They will also fill this region here with its electric field lines. And so what you have in the interior region there is you have a superposition of electric field lines because of the positively charged plane and the red arrows, and the negatively charged plane and the green arrows. Now we know the electric field due to one plane here is sigma over 2 epsilon, but we have 2 planes now. So the total electric field in there is going to be sigma over 2 epsilon because of the positively charged plane plus a sigma over 2 epsilon because of the negatively charged plane. And again, sigma here is charge density. This has a sigma on it and that has a sigma on it. And it's very tempting once again to say this sigma should be negative because it's a negatively charged plane, and this sigma should be positive because it's a positively charged plane. And you'd be correct in saying that, but then you'd mess the directions up. We've already implied the signs and the directions by drawing these arrows in here. Both electric field directions due to the positively charged plane and the negatively charged plane point up this way, so we have to assume these are going to be positive sigmas, and this is a positive sign. Mathematically, this sum statement here matches with the fact that both these arrows are pointing up in the same direction. In either case now, the total electric field at all BC between the plates is just sigma over 2 epsilon. And this is your key result that you need right here. Sigma over 2 epsilon. What it tells you then is that when you have these 2 oppositely charged planes, there's an electric field between them. And that's the key to getting this problem solved here. Because if you launch an electron in a region where there's an electric field, it's going to feel a force. So the thing that's actually getting launched here is an electron. So I'll just draw a little electron in there and it's going to get launched. Now what happens? Does it go straight or does it curve? Well, it's in an electric field. So the force that the electron is going to feel is going to be minus Q because it's a negative charge electron times the electric field, E total. So the force it's going to feel is going to be minus Q times sigma over epsilon. The electron will feel a force now. You can work on this a bit more, remembering from physics 141 that F is equal to ma minus Q sigma over epsilon. So the acceleration that the electron feels now is minus Q sigma over m times epsilon, where m here is the mass of an electron. You can look that up in your book. It's 9.11 times 10 to minus 31 kilograms. But you put a big box around this, and what you realize now is that the problem has just been reduced to essentially a physics 141 problem where a projectile is being launched above the ground. Because you remember from physics 141, you had a whole bunch of problems that maybe there was like the Earth here like this, and someone would come in here with a baseball, and at 45 degrees and some speed v naught, they would launch the baseball. It would execute some sort of parabolic trajectory because you knew that the acceleration due to gravity was causing the object to fall, and it was all due to little g. Well, we don't have little g in this problem, but we do have something that behaves just like little g. An A, which is a minus Q sigma over m epsilon, presents a downwards force on the electron. So this is essentially a projectile problem from physics 141, but instead of 9.8, you have this acceleration pulling the electron down. So as the electron flies between the 2 plates, here's the top plate and here's the bottom plate. Here's all those negative charges and here's all those plus charges. The electron is launched here. at 45 degrees with a speed v naught, and at all times during its flight, if the electron is right here in its flight, it's feeling a downwards acceleration a that's given by this formula right here. So in between these plates, the electron will execute a parabolic trajectory just like the baseball did from Physics 141. And so I think you can recast the problem in terms of that sort of thinking. Now, it's a projectile motion problem here. You have a certain range and a certain height you want it to achieve by not hitting the top plate or whatever the problem happens to call for, but you have an A instead of a 9.8. So, for instance, you could do something like Vy is V0y minus Q sigma over M epsilon naught times delta T. This is how the y component of the velocity electron would evolve. And remember, in Physics 141, this term right here would have been g, or just 9.8. But in Physics 133, it's Q sigma over M epsilon. And the other equations can be used. This acceleration can be used in the other equations of motion in a similar way.